if you clicked on the thumbnail and you are now watching this video, as an engineer who builds stuff, first things first, a tool is only as good as the hand that wields it. Of course, it's just copium for those of us with bad or subpar or mostly less than desirable tools and working conditions, but it has merit because a bad engineer with a good tool can achieve maybe a 5/10, but a good engineer with a good tool can achieve a 10/10, or even with a bad tool can get up to a 7/10. Of course, with a lot of nuance to it, but you get what I mean. So for those of us, including me, with what I'll call an okay but subpar 3D printer that, I kid you not, isn't even supported on Creality's new Creality Print Slicer software, it is essential that you master your machine. Dial in your settings to be the best you can get it to be. Take the time to know its tolerance, its preferred print speeds, what makes your prints have stringing issues, how to solve your temperature problems, and what works. You need to know what works and what doesn't. Essentially, I'm saying get good. I'm probably dialing your settings, but all in all, here's my workaround in both the design and printing process that still helps me even when working with better machines, and probably if you have a worse machine. Either way, these are the processes that help me in the designing and the production of my very own prototype parts, which you can apply also. But in this case, we'll go with a product casing that I made for the iteration of a product that's currently being installed at the location it was made for. Since you're watching this video now, it means you clicked on the video thumbnail, and that plus the caption was enough to draw in your probably short or long attention span, which, one of the following. It means that you need to design a product ASAP, you want to find out the simplest process for that, or you're a tech bro or girl just like me and you consume tech videos while you're eating and you wanted something to entertain yourself. Or, most unlikely, you're a subscriber of mine, which is less than 95% of all my views. So if you'd like to be against statistics and unique, why not subscribe, leave a like, and if you enjoy the content, drop a comment on your favorite tip or trick from this video as I'll reply to them all. The case scenario for this video is that you already have some electronic parts and components for your prototype, so what you need is an effective housing. The product I'll be using to explain this has no mechanical or moving parts, which leaves us a whole section for the design tips, but most of this will still apply to them in terms of how the tips and tricks work. First task is to do a draft of what the final design is, including any requirements and methods of assembling the final product. In this case, I had to have the screen coming from the front in the assembly process, and its corresponding mount or support plate would now have multiple openings which will allow for wiring to pass through it. Now, this is outside of all the necessary components, including a speaker, fingerprint sensor, NFC/RFID scanner, a switch, and 2-pin GSC connector holders. Once you have the general concept of the design, the next thing is to measure all the components and get the dimensions of the components. In this case, I measured all of them that I previously mentioned. Now, here's the thing with measurements: tolerance. We have an RFID or NFC scanner, and based on the design draft, it needs to fit in a slot. So how do we make that happen? Using a vernier caliper, I measure the dimensions of the RFID/NFC scanner, and let's say the measurement is 42 by 40 millimeters, and it needs to fit into a slotted hole. It means that the hole needs to be just large enough to allow the scanner to fit, but not too large where it's loose and it just flops around. You can also use the mounting screws for ease, but we are not doing that in this case. From previous testing and experience, I know my printer's tolerances and what they are like. For example, 0.2 millimeters is tight fit to not working, 0.25 millimeters is a great fit and an okay fit, and 0.3 meters is a loose fit. Now, I know there's newer printers there with tolerances of 0.05 millimeters or 0 millimeters even, but I don't have that. I have a Creality CR6 Max. Therefore, after drawing up the components which are at the front of the plate of the casing, which included the fingerprint sensor, the screen, and NFC scanner, I added tolerance values to them so that they can have slots that they actually fit in, and then I extruded the faceplate and then all the slot walls. With the extruded faceplate section for mounting the screen and the corresponding section cut out for wiring, the next thing I did was to extrude the actual walls of the casing which go down to the base. The base itself was pretty easy as it just needed to hold the circuit board as a mounting plate and then the fingerprint sensor. I also had to model the hooks for the 2-pin GSC connectors so they could actually just slide in and still have room for wiring. but would be restricted in moving only in one direction. So you could slot them in, but they wouldn't move back beyond that. On the topic of walls, another thing to consider when 3D printing is strength requirements. In order to have a part for a prototype that is strong enough for use, you can consider the wall thickness in your design process, and then you can also consider the infill density in your slicer, as this pretty much are directly proportional to the strength of the 3D printed part. I know print orientation is one of the most important things when it comes to strength, but I'm guessing there. For this part, I needed to use the least amount of material possible and the most strength I could get from it. I usually make parts around 3mm thickness, but that all depends on you. For this one, I went with 2.5mm wall thickness and a 3 wall line count. You can also improve strength by having a higher infill percentage, changing the infill pattern, increasing wall line count, and these are all settings in the sizing process. But note that all of them will definitely affect your print time, either positively or negatively. So the way you either you increase or decrease them might give you more or less print time. With the main section for the faceplate and the different components done, I worked on the screen holder, which is an extrusion that was done inward and has mounting holes to allow the screen to be screwed onto it using M3 screws. For ease of printing, after the first print of this part failed, I went through a couple of iterations, as the first time it was attached to the main body and printed with support, but that didn't work so well. So next, I cut it off and made it into a sliding part so that it could actually fit in and would be glued separately. I personally found that the best glue for me particularly and what I had access to was between super glue and 2-part epoxy glue, which personally for me was the best, as it became a part of the structure and had quite a lot of strength even compared to the super glue, especially because of how when it cures it stays really well when it's set. Now let's talk about fasteners. When dealing with screws, there's two major options I use. One is to self-tap the thread yourself into a 3D printed hole, while the second is to use heated insert. And for most use cases, as the broke engineer I am, I use the self-tapping screws into the 3D printed plastic, especially when the print has good wall thickness and a decent wall line count. It works really well, and for moderate strength fit parts, it's good. Now, of course, an M3 screw has a 3mm diameter, so I usually print a 2.9 or 2.8mm diameter hole for a tightly fitted screw that holds tight, and sometimes I put a 3mm hole depending on just the material and also the tolerances of what I'm looking for. I also make sure that there's sufficient material surrounding the hole, like in this case where I made the extrusion to support the hole and chamfered it in, so I wouldn't need support to be printed. Print orientation. This is, if not the most important thing to be done in the printing process. Taking your 3D model to your preferred slicer of choice and putting in your print settings. The hierarchy for this, in my opinion, is dominated by the print orientation. Whenever you're considering the functional parts, for example, printing a part that would be stressed along the X, Y, or Z axis, that would change how you orient the printed part in order for it to have the most strength to counter against the forces that you're expecting to be acting on it. And this is all due to layer lines being like the weakest part. So this is the actual con of additive manufacturing in FDM printing. There's a bunch more tips and tricks I would like to talk about pertaining to the design, but this was supposed to be a short tip and trick video, but ended up just being a how did I do this for now kind of video. But if you'd like me to do more videos like this concerning 3D printing and production processes from idea to product, which also involves electronics, embedded systems, and robotics, which side note, there's a lot of robots coming, and maybe I'll do a 2-part of this to complete all the tips and tricks. Now, on the other hand, after slicing with all the other parameters and settings dialed in, like I talked about before, I got to printing. But before that, I want to tell you about today's sponsor, PCBWay. PCBWay isn't just a company that manufactures only PCBs, like their name implies, and if you're like me, who didn't have a 3D printer until recently, and you want to get manufactured parts of exceptional quality, well, look no further than PCBWay for you to get your parts manufactured and 3D printed. Of course, they have a variety of manufacturing services, ranging from CNC machining to 3D printing, sheet metal fabrication, and injection molding. You can go to their site linked in the description, upload your file, select the print parameters, material, print technology, and get a quote and some high quality printed parts for your next project. I want to say thank you to PCBWay for sponsoring the video, as they've all actually contacted me 3 years ago, but kept up with my horrible posting schedule while still allowing me to collaborate with them. Once again, I'm grateful to them, and most importantly to all the subscribers who have made this small channel as successful as it's gotten. Albeit small, but we're building something great. There are many more robots to come and work in the future, so stay tuned subscribe and leave a like. Now back to the video. I set out all the parts for the assembly. And then placing the RFID or NFC/NFC scanner in its slot on the faceplate, and as you can see, it's a snug fit. Next, on the base plate, I placed the hand-built circuit at the center in its own slot, and then the fingerprint sensor in its slot. After that, I put the DST connector in its slot. To test if the screen mounting plate fitted, I slid it in and mounted the screen onto it with the screws. In the process, I realized that some of the screw mounts needed to be offsetted by a certain or little amount so that they can actually be precisely the location they needed to be for a proper fit. After that, I printed the logo's text in a different color, which was orange, and they were printed with a tolerance of 0.2mm to the extruded slot in order for it to be able to have a tight snug fit. But I still used super glue in extremely small amounts to secure them in, and I did the process multiple times to have more than one case, and that's how I arrived at the final product casing. Now I know there's a lot of missing parts, questions to be asked, things I didn't talk about, but I'm currently working on the next robot. So in order to have sufficient time to work on that video and release it ASAP, I had to cut on the volume of information that I put in this video. Feel free to ask any questions in the comment sections. I'll answer all of them. And with that, like, subscribe, turn on post notifications if you made it this far, and Godspeed. See you in the next video.